So how does one find the minimum or maximum of a function, of a nonlinear function? Well, the minimum of a quadratic function is actually quite easy to find. We can compute this in a closed form, given that certain conditions are satisfied. So if you have a quadratic function in m dimensions, where this is a general quadratic function in m dimensions with some constant c plus g transpose p plus half p transpose hp. Okay, so this is the general form for the quadratic function. Of course, g is not necessarily uh, the gradient at any point. This g is actually the gradient at p equal to 0. In any case, um, this is a general form for a quadratic function in m dimensions where f itself is in R, p is in Rm, g, because it's a gradient with respect to p, is also in Rm, c has the same sort of dimension as f because, well, it's sitting in equal status with f. In H, like we discussed, is an m by n matrix. Okay. Um, if we assume that H is a positive definite matrix, right? In other words, its eigenvalues are all greater than 0, then this function has a minimum, it turns out. It has a unique minimum. If H is negative definite matrix, then it's got a unique maximum. Um, in any case, if it does have a positive definite Hessian H, then how do you find the minimum? You differentiate this function, set it equal to 0. Differentiation in this case is the gradient of f. Gradient of f with respect to p, it turns out is just g, and then the gradient of this quantity is h times p. And this is something that we mentioned early on in the course when we were deriving an expression for um, like the pseudo inverse for linear regression. We mentioned how to take the gradient of a function that looks like this. So you can look back at the notes from there. So suffice it to say that the gradient of this function is just this function, and we set it equal to 0. You can rearrange. You can say hp equal to minus g, like so, and then p is going to be minus h inverse g. So if you have a function like this, the way to find the minimum is basically use this formula, right? So if you have a quadratic function with a minimum, then the minimum value, the minimum point is given by this expression. Okay. Now, of course, the quadratic function is a very, very special kind of a function. Um, what if we have a general nonlinear function? For general nonlinear functions, it's usually not possible to obtain an analytical solution for the minimum or a maximum. So we resort to numerical methods. Examples include, well, you may have heard of some of these methods. Gradient descent is one of them, which we will look at in a minute. Newton's method, and it's upon this method that Fmin-Unc in MATLAB is based, which is something that we've already used. There is a method called Nelder-Mead simplex, which is the basis for Fmin search in MATLAB. All of these and many, many more are all methods for unconstrained optimization. In other words, the unknown p is not necessarily constrained. It could take any real number if it's in one dimension, or any value in Rm if it's in m dimensions. Okay, so these are methods for unconstrained optimization. They may be modifiable to constrained optimization, but their core is an unconstrained method. There are methods, more sort of elaborate methods for optimizations in the presence of additional constraints, simplex sequential quadratic programming, interior point methods, etc., etc. Again, there are like many tens of methods. Fmin-Con in MATLAB implements actually some of these methods. Um, okay. I just leave it at that, and I will do a brief tutorial on FMNCon that I will post. Okay. The next topic is actually studying this most basic of optimization methods for unconstrained optimization called gradient descent. Okay, so what is gradient descent? Like I said, it's the simplest method for unconstrained optimization. The basic intuition is as follows. I usually ask people to close your eyes and imagine that you're on an uneven terrain, kind of a mountainous terrain, um, and you want to go to the lowest possible point in that landscape, right? So I ask you to close your eyes because, or assume that you're blindfolded, because these kinds of optimization methods cannot see the whole landscape, cannot see the whole function, the whole sort of surface plot of the function, right? Similarly, if you're in this landscape and you're blindfolded or you close your eyes, you cannot really see where the mountain top is or where the bottom of the valley is. And that's kind of the situation that these optimization methods find themselves in. They cannot see a global picture. All they can do is kind of um, search locally. And gradient descent does the following thing. Going back to your analogy of sort of going to the lowest point of this landscape, gradient descent basically takes a imagine you're in this landscape and you sort of do probe experiments with your feet. You take a step perhaps in all directions, just as a thought experiment, and then you choose the step that gives you the greatest um, descent, greatest reduction in your function value, right? So that's kind of like gradient descent. You want to step in the direction that the function value decreases the fastest. Okay, so that's gradient descent. And then you keep doing that until hopefully you reach the lowest point or until you cannot reduce the function value or the height any longer. Okay, so more formally, this is the method. Imagine you're trying to minimize f of p, where p is an Rm. We are really stepping in m dimensional space, um, right? So you're doing the stepping business in m dimensional space as opposed to 2D or 3D. It turns out we can show mathematically that the direction of steepest ascent is gradient of f. The direction of steepest descent is negative of the gradient of f. Okay, so of course the gradient and the negative of the gradient belong to Rm, so it is a step in Rm, which is what we want to do. Okay, so what do we mean to say when we say direction of steepest descent or direction of steepest ascent? Um, if you take an infinitesimal step, if you imagine taking an infinitesimal step in every direction in this m-dimensional space, starting from a particular point, it turns out that if you step along the negative gradient direction, you will decrease the function value the most. Okay, this is true for an infinitesimal step. Okay, so that's the direction of steepest descent, and that's what we want to follow in the steepest gradient descent method. Okay, sometimes it's called the method of steepest descent as well. Um, okay, so now, how do we sort of operationalize this idea in the context of iterative method? And this is how you do it. Let's say you want to find p star at which f of p is minimized. You start somewhere. You make an initial guess about where the optimal value of p is, and we're going to call that p of 1. Okay, so this is not the first element of the array P, but rather the first iterate of uh, P, right? So this whole thing we're going to call the initial seed. This 1 is the iteration count. Okay, so P of 1 itself belongs to Rn. So you start somewhere. maybe it's a random initial seed. And then on the ith step, you basically, if you have p of I, you take p of I, you compute the gradient, take the negative of the gradient, multiply that by a small number alpha. So this is the step we are going to take. So this is your guess of the optimum, or the best attempt at guessing the optimum, I guess, on the ith step. Then you're modifying that by taking a little step along the negative gradient, okay? And then you get pi plus 1. Then you keep doing that until uh, some condition is satisfied. For instance, the difference between pi and pi plus 1 is not very much, or the function value doesn't change much, etc. Okay, or maybe most sort of precisely, the value of the gradient is actually very close to zero. If the value of the gradient is very close to zero, then of course we know that we are very close to a minimum. So that's the method. You start somewhere and then keep doing this, where you take where you are, add some small multiple of the negative gradient, and keep doing that. Okay, so that's gradient descent. You repeat until convergence. Now, once you have an equation like this, you might ask, how should you pick alpha? So alpha is sometimes called the learning rate. It's kind of analogous to a normalized step size, step length. Um, it's like how much to step along this negative gradient direction, is kind of what alpha is saying. How aggressively do you want to step, right? Um, okay, and this is of course the negative of the gradient. Um, so how to pick alpha? The You have a couple of different choices. One is to pick it small enough so that you ensure that you will decrease the function. Another is to actually choose different values of alpha and see which alpha value minimizes the function the most. That procedure is called a line search. A lot of classical optimization methods do that kind of a line search. Uh, Modern machine learning algorithms do not use line search because they don't want to evaluate the function too many times. Okay, so we will just pick a small enough alpha and hold it mostly constant, and then we'll talk about how to change alpha later. So that's about alpha. And then how do you compute the gradient? There are a few methods for computing the gradient. Um, some are numerical, some are analytical, some are sort of in between. Um, some are high accuracy, some are low accuracy. In any case, it just has to do with differentiating the function with respect to p. And that's an important aspect of the gradient descent. Okay, so those are two things we need to do. Um, and the next video, we will actually just assume that we've picked an alpha and are able to compute the gradient effectively, and just implement gradient descent on that function.